now. And then we can talk about a few of these. So we have 7 diagrams that the book is going to show us. As I mentioned, number 1 is not really that important, all right? And if you look at figure 1, remember I don't have pages, so if you look at figure 1 in the book, there are some things about as I said, a pictorial or picture or a drawing, however it is that you want to say that for yourself. Pictorial is how they're calling it. There is some things about this that is beneficial. Where is it really beneficial is here, right now, when we're looking at a book, right? When we're being introduced to new components and new parts. Sometimes a picture is very helpful. All right, now obviously we're in class, so we do get to see a lot of the components in the physical sense. But if you're, looking at a new component, you have not seen it before, a picture is good. So what does a drawing show us? This is, or should be, in some ways obvious. It gives you dimensional space, right? It allows you to understand the dimensional space that whatever it is that they're showing you takes up. All right, in this case, they're breaking down a flashlight for us with the battery and the switch and the light. All right, not too complicated, beneficial maybe in some ways, but I would say, as an industrial electrician working with machinery, I honestly have not had a lot of use for something like this. All right, maybe once in a while to identify where something is at on a machine and they have the whole drawing of the machine, then maybe. All right. So for the most part, we can go ahead and ignore number 1 as something that's useful to us. So it really starts to be beneficial to us from that point forward. 2, 3, all the way down to 7. Now again, this is about language of control. All right, meaning there are a few diagrams that they're talking about here that are kind of the same thing. In fact, 2, 3, and 4 are in many ways the same thing, especially 2 and 3. So let's look at what the book is showing us for 2 and 3. We're going to jump ahead a little bit over to figure 2-3. The next couple of figures are showing us symbols, which right now we're not going to get into symbols yet. If you're following along with the book, they're jumping from the pictorial drawing right over to symbols, and I want to leave symbols for after we cover all 7 of the diagrams. So jumping ahead just a little bit over to figure 2-3. All right, and this has a diagram for you to be able to follow. Now, what they're showing us here is, and I love this, this is a electrical motor controls book, and they're showing us a waffle iron, which that doesn't even look like a waffle iron. I guess it's a waffle iron, but it looks a little bit like a briefcase. Not so much a waffle iron. But we do have a wiring diagram down there on the bottom, which is showing us a few things like the power coming into this circuit. It's showing us a switch. It's got a symbol. That symbol that you see with the little line around the switch part, that's a temperature switch. And then we have what they're pointing at, a couple of heating elements, the upper and lower heating element of the waffle iron. Now, are we going to talk waffle irons in this course? No. So let's head over to the paragraph and just get a few notes out of here. So as it says here, a wiring diagram is designed to show, all right, it's a diagram that shows the connections of all the components in a piece of equipment. These diagrams, as closely as possible, try to show you the actual location of each component in the circuit. And it goes on to say that wiring diagrams also include, or often include, details about extra things. Wires, the hardware we've used, any kind of termination, connection point. But because we don't study waffle irons, I also have a note here that I want to make sure that you guys have for wiring diagrams. When it comes to our world of motor control, and I'll show you a wiring diagram here in a second, this is how we want to understand a wiring diagram versus a schematic or ladder diagram of the green ones that I have isolated here. So in our world, the wiring diagram shows us all the components being used, which they are telling us that. All right, it is saying connections of all the components in a piece of equipment. But more so for motor control circuits, as we were talking about yesterday, a wiring diagram is going to show you power and it's going to show you the control circuit at the same time. I'll be right back to this if you are writing it down. We looked at the wiring diagram yesterday, which was this one. This is a wiring diagram. All right, the wiring diagram, again, it's showing us first of all, it's showing us everything that's in play. From the fuses to the transformers to the motors to the motor starter, all the controlling devices, grounding of the system, right? It's got all of the labels for everything. So it's not just a bunch of lines, it's got a lot of information that goes along with the lines. Also, it gives you the entire, right? It gives you all of the components being used in a piece of equipment. When I show you a ladder diagram, you will see the difference between these two. So wiring diagram shows you all the components. In this case, we have, like I said, we were going over this yesterday, so you should have some idea. We have the power. We have the fuse line disconnect. So if we were troubleshooting this, then we'd know, all right, we got some fuses we got to deal with on the power side. We have a transformer we have to deal with on the power side. We have a control fuse that's going to come into play on the control side, and etc. I have a start button, stop button, but that's all I have. I don't have, all the other devices that I just showed. I don't have a pressure switch. I don't have a temperature switch. I don't have anything else. This is all the things that are in play. So if this motor's not working, I have an idea of how to fix the motor, not just on the control side, but also on the power side of things as well. All right, so that's a wiring diagram. The other one, and by the way, this is the catchword that everybody uses for all diagrams. You'll hear people use the word schematic a lot. Right? That's kind of like an umbrella term in many cases for any kind of industrial machines diagram. Everybody just likes to say the word schematic. But schematic is specific. All right, now let's head back over to the book. We're done over here with wiring diagrams. So now we are going to follow the order that the book is providing. We're not skipping anywhere. So we're going over the next figure. And this looks a lot like a waffle iron. Right? There's the waffle iron diagram. Right? Let's look at that one more time. Right? We have 120 volts. It's showing us a plug, meaning that we're plugging this in. We have a switch so we can turn on and off our waffle iron. We have a temperature switch. That's what that little symbol is right there, right below the word lower heating element, that first one. That's a temperature switch, right? Because the waffle iron has to come up to temperature. So one of the things that is part of this system is if this waffle iron has not come up to temperature, then things aren't, or if you haven't set a temperature, I should say, for the waffle iron. I'm not a expert on waffle iron, so I'm trying to guess how this thing works in a sense. If we look at the schematic right up, it looks a lot like that waffle iron we just saw. 120 volts coming in. We have a switch. We have that same little symbol, and we have those two heating elements. So what's the difference? Well, as it comes to the diagram, actually none. There is no difference between that diagram and the other diagram. So that's why I showed you the diagram that I showed you for a wiring diagram. Because for motors, a wiring diagram is the kind that's going to show you what's on the power side. Going back over to it, all right, so I have a three-phase motor, so it's AC, three-phase. The motor is not DC, so I got that. The motor is not single-phase. This is not a single-phase motor. This is a three-phase motor. I can guess more or less the voltage, but doesn't really matter. Also, I have a transformer, meaning my control circuit is still AC voltage. So we get a lot from this diagram. Now, going back over to the schematic, what's the difference? Well, let's read what they have down here in the paragraph, right? Specifically that first sentence there. Schematics are intended to show the circuitry, and here's where it becomes specific to when you're going to use the word schematic. when you're talking about the operation of a device of some kind. Now, here the word device, I think it's a little bit misnamed. I think better would be the operation of a piece of equipment, all right, or the operation of a motor, or the operation of a tool, or the operation of something like that. All right, now the word device, I guess it's fine overall, but a lot of times when it comes to electrical work, when we hear the word device, we're thinking switches, we're thinking things like that. But I am using it, so I don't have a lot of a difference between this one and the one in the book. Shows the internal operations of a device. So for example, if I open up the connections to the washing machine, right, where I open up all of those control components, on the washing machine itself, it's going to have a diagram. That diagram is not called a wiring diagram. That diagram is not called a ladder diagram. That is a schematic, because the washing machine is a device. All right, it's a piece of equipment. That's why I said the word device a little bit misused there. If I want to find out how a drill works, and I want to open up a drill, and I want to fix the drill, well, I pull up the schematics for the drill. If you want to open up a computer and figure out what's going on inside the computer, you pull up the schematics for the computer. So anytime you're talking about the internal components, all right, that's why I have that word there versus what they're showing us in the book. The book did not give us the word internal. All right. So not the power coming to the motor, or not the power, I should say, coming to the machine, but inside the machine itself. All right, so if you're opening up whatever type of machine and you're trying to figure out what's going on inside, there again, we are talking simply the language of control, so that's called a schematic. Now, I'll show you a schematic. I have one here. Let me minimize that one. It is a little bit large, or actually my... All right, and this is a car, by the way. This is a schematic for an automobile. All right, you see ignition coil down here. You see distributor. All right, for folks familiar a little bit with cars, you know, you have the horn, you have the parking lamp. All right, this is a schematic. All right, if you were pulling up the electrical diagram for a car, technically the correct name for that is schematic. All right, now, same in a sense, right? We have a bunch of symbols, we got a bunch of lines collecting to the symbol. Here's our ground, so a lot of familiar symbols. All right, here's another ground over here as well. We got what looks like semi push button over here. So a lot of familiar symbols versus, you know, just being about cars. So in a way, you can, if you understand how to follow these diagrams, you could troubleshoot this car and figure out why something is not working. Like, for example, something as simple as finding out why the dome light is not on. Well, you can follow it back, find that switch, figure out where that switch is, see if that switch has power, work your way back, and so on, the same way that you would with a wiring diagram. However, two differences. Wiring diagrams are for motor control circuits, and schematics are for pieces of equipment, for lack of a better word. I don't like the word device, and I don't have a replacement word for it, so I'll just go with device. That's fine. All right, good so far? So sometimes we're in the business of working with a wiring diagram when we're looking at a motor control circuit. All right, there is a benefit to a wiring diagram. Again, it gives me a picture as to what the power coming into this control circuit is going to be. So that is important, especially if you don't know. All right, if you're working somewhere new and you don't know what, you know, voltage is going to the motor, or, you know, you don't know if there's a transformer in the way, or is there a power supply stepping this down to DC voltage? Is it three-phase? Is this disconnect, does it have fuses or does it not have fuses? Sometimes these disconnects here don't have fuses. A lot of times they do for motor control systems, but sometimes they don't. So a wiring diagram is good because it gives me a window into the power side of things. However, here's how this job goes. A lot of times with these jobs, we're not showing up somewhere for the first time and troubleshooting their machinery. Right? Most companies that I'm aware of hire in-house industrial electricians. So they're not calling an electrical company to go, hey, my machine just broke down, and so electric shows up and go, which machine? This one. Well, I've never worked on that before. Do you have the diagram for it? Yes, here's a wiring diagram. All right. Oh, I see it's a 3-phase motor. It's got a fuse, and it's not how it works. All right, that would be really inefficient for a company to do that, and they'd be spending a ton of money on electrical companies showing up all the time because machines stop throughout the day multiple times. So instead, you hire in-house staff. So the first time you work on a machine, yes, you're not aware of how things are distributed as far as power goes. But as you work on machines over and over, you've been at the job for a month, 2 months, 3 months, 6 months, a year. Well, now you're familiar with a lot of the way power is distributed to the motors. So you don't need, in most cases, you don't need the power side of things. Power doesn't really change, you know. Once you figure out that there's a disconnect with some fuses and a transformer, that stuff's not going away. It's not changing. It's not moving around. Nobody's moving it. So you don't need to get that diagram all the time. So for that reason, most of the time, when we're going to troubleshoot a machine, we're worried about the control circuit. All right, we're worried about the control side of things because here's where problems can happen in multiple ways. Now, this one is not too complicated. It's a push button start stop, so not too many things can go wrong, but you know, I can lose the fuse, push button might be out, coil could be bad, one of these folks could be open, etc. We'll get into all the different things here. Now, if I had more things going on with this motor, like pressure switches and sensors and all kinds of things that have to effectively be engaging for this motor to start, then you can understand why I would want to focus more when a machine goes down on give me the control circuit. That's what I want. I want a diagram with the control circuit. I do not care about power right now. So for that reason, they made one. All right, we'll go on to the next image that we have, 2-5. And here we get to the diagram that for the rest of this module and for next module when you go into PLC, you will be working with. And in PLC, you'll be designing these, which is our ladder diagram. I know the book likes to use the word line diagram, but we do not call it a line diagram in this module or at all in this industry. I think everybody that I'm aware of calls this a ladder diagram. All right, so real quick, we'll zoom in on our ladder diagram here. You can see a lot of what is on my whiteboard on the wiring diagram, right? Look at the wiring diagram that I have here. Red arrow pointing to the control side of things. Very similar. We got push buttons, we got coils, we got etc. This one has it as well. It has a couple of extra things, but there's our start button. There's our stop button. We got some open and closed contacts here. In this case, we have a light. We do have the starter operating coil. All right, now this is hard, by the way. This is why I say bring the book, because sometimes on my whiteboard, this is hard to see the details of it. Like you might not be able to understand a lot of what these words are saying, so the book in front of you is way better. But we do not, if you're looking at this ladder diagram, we do not have a window into power. I don't know about the power side of things. I don't know if the motor is 3-phase or single phase. I don't know if a transformer is feeding into this control circuit. Maybe it's not. Maybe it's a power supply. So maybe the voltage here is DC voltage. I don't know if I have a fuse, right? We don't have that little fuse that's over here. I can assume, but I don't have it. All I have is the control side of things. So if I'm troubleshooting this, this is the most important part, but again, if you were concerned with the power side, then you would need a wiring diagram. All right, main difference. So wiring diagram has the control circuit. Ladder diagrams do not have the power circuit. There's a great question to ask for an exam. Main difference between wiring diagram versus ladder diagram. Again, wiring diagrams have the ladder, but the ladder diagrams do not have the power side of things. All right, let's go over here to the paragraph. Again, if you're not finding the paragraph, let me know. But it says the ladder diagram is a diagram that shows the logic, right? There is our L in PLC, programmable logic controllers. All right, logic of an electrical circuit. And we're going to get into logic when we get over to chapter 5. But basically it means how the circuit is built. All right, how the circuit is built. What things are in series with each other, right? The stop button and the start button, they are in series with each other. What things are in parallel with each other? The start button and the normally open contact right below it. These are in parallel with each other. All right, chapter 5, we'll get into better describing that, into logic functions, things like and or. If anybody has ever done logic gates, kind of the same. So there's the important part that we want to understand about a ladder diagram. It shows us the logic of an electrical circuit or system using standard symbols. A ladder, again, it says line, but I'm going to just say ladder diagram is used to show the relationship between the circuits and their components, but not the actual location of the components. Now, that's basically the note that I isolate for our ladder diagram is that. All right, so you can highlight the book, or you can write this much more consolidated note. It shows the logic of the circuit. If you wanted to write motor control circuit, that'd be fine too. All right, so ladder diagrams show us the logic of the motor control circuit. And again, logic is just a fancy word for how things are wired up together. All right, and they can only be wired up in two ways, series and parallel, but then there's combinations of those. Now, you guys have seen some ladder diagrams. I'll show you a ladder diagram here. I like this one because it's a little bit more complicated than the ones that you're working with on day 1 and 2. So this is a ladder diagram as well, right? We have L1, we have L2. This is very standard, and we'll get these notes in a little bit when we just talk about the ladder diagram. If you look at the diagram here, same thing. We have L1, we have L2. Right, in fact, we could write a couple of notes on the ladder diagram just while we're here. All right, because I am going to be missing a day, so I don't have a lot of space to. So when we're talking about a ladder diagram, so first thing that is obvious is, again, I do not have a window into power. I don't know what's feeding this. Right, I don't know if it's, again, AC, DC. I don't know if I have a transformer. I don't know if I have a fuse and all that stuff. But 9 times out of 10, the problems aren't on the power side. 9 times out of 10, the problems are on the control side of things. Right, and here we have some different symbols. Actually, I'm not actually sure if this is a US. It is US because US, the ladder L1 and L2 drop that way. All right, they're vertical lines. And European ladder diagrams, L1 and L2, are horizontal. So I know it's American, just the symbols are a little bit different from the ones that we standard use. So while I don't know, right, what L1 and L2 are, again, the power coming into this, here's what I do know, all right? L1 and L2, they represent power. All right, these are the representation of power coming into this circuit. Meaning, this entire line, and we'll imagine this is all connecting all the way down, this entire line here, and this entire line here on this side is the power coming into this circuit. So anything picking up power from that line is picking up the power coming into this circuit and sending it into the rungs. All right, we'll get all these names here in a second. So L1 and L2 represent the power. L1 is always hot. Or, because we will be building enough, not a lot, but some labs with DC voltage positive. So again, while I don't know if this is 120 or if this is 24 volt DC or 12 volt DC or 240, it can be 240 as well. There's all kinds of voltages for motor control circuits. I do know that everything coming off of the L1 side is positive, or again, hot. Meaning L2 is the other side, neutral or negative. Actually, I'm going to change the color here for this one. Now, 100% of the time, never, ever, ever will it be different. L1 is on the left-hand side, L2 is on the right-hand side. Right? Always. Never do these two interchange. Right? L1 is always on the left, L2 is always on the right. So, what divides the circuit in half, right? Where is the half, where is the middle point of this circuit? Where does L2 end and where does L1 start? And it's going to be at the load, all right? I'm going to try to fit this whole note down here. Let me slide this over just a little bit to create some space. Circuit is divided at the load. All right, circuit is divided at the load. So anytime you're looking at a ladder diagram, and this is why you guys are going to be designing some of these ladder diagrams. A good idea to, anytime you have a load, which is always represented as a circle, we'll get into the symbols in a little bit. It's always best to put them all lined up together. It's just easier for whoever has to read this to be able to make sense of it. All right, now you guys are designing your own diagrams and you're building your labs to your own diagrams, so you know what you're doing as far as how I wrote this. But remember, and always keep this in the back of your mind, this is why when we turn in our labs, you guys turn in the diagrams, because I will be looking at the diagrams and I will be giving some notes along the way if I see some stuff that just looks wild. One of the first things that I kind of look at is that. Do you have a load over here and then the other load's over here and then the other one down here? This becomes so annoying because it's hard to now figure out just by a quick visual as to where things are, because the circuit is divided at the load right down the middle here, and this one's perfect because they're all lined up together. Now I know exactly where L1 ends. L1 runs all the way up to right there on that load. That's L1. We can skip that little funky thing that's going on here. L1 right to there. This is all part of L1, and this is all part of L1 here. So all of this should be hot. So anywhere along the line on this ladder diagram that I check for voltage, I should be reading voltage. Meaning L2 is in the other direction. That's why I changed the colors here so I can be able to. L2 runs to here, to here, to here. And you can see L2 is not doing a lot. It's a neutral or a negative, so not a lot going on there. L1 hot, that means all of your switching components are on the hot side. Just like for our standard electrical circuits, nothing is on the neutral. All of the opening and closing of the circuit is done on the hot side of things. All right, questions? Good so far? Everybody following along with no issues?
Why did you skip the MCR thing?
The MCR.
Yeah, between 105 and 110 in the first top box where the push button is.
Sorry. I thought you meant in the book. I'm like, wait a second, because I know I skipped the symbol, so I was like, wait a minute, why did I skip the? I didn't, not for any reason. It just gets a little bit complicated. But yeah, all of this would be hot as well. This is just a very odd way to have drawn this with that little gap between them. It's
Okay,
fine in a sense, but I don't like that.
got it.
Yeah, I like our ladder structures to be ladders. This is why we call them a ladder, because they have two rungs on each side, or sorry, two rails. They're called. We don't need to get into the names, but that's what they are.
Got it. Understood.
Yeah, but yes, this would all be power as well. Very good. So not only, right, two things. One, not only am I almost all the time, 100% of the time, 99% of the time, troubleshooting on the control side, so I don't need a wiring diagram with the power side of things. Also, I'm generally troubleshooting on the L1 side. Right? If things aren't turning on motors, in this case, we have a pump down here, right? We have some labels. We got a pump. If that pump is not on, yes, I want to make sure that there is power. So obviously, I'm going to check power between L1 and L2. I'll check between the hot and the neutral, or the positive and the negative. Usually this is located somewhere along the points of, like, for example, just to pull up the classroom, and so the online students can get a look at what you guys are working with. Where's L1 and L2, right? We just got a piece of paper that says L1 and L2. So this is what I was saying yesterday. Motor control lives on paper, and it lives in the physical sense. So looking at a piece of paper that says L1 and L2, now where do I find this on? Obviously, Phil is walking you through a lot of this, but L1 and L2 will be located at a specific point. So I can measure my voltage between L1 and L2 there, confirm that I have power, because if I don't have power, it's just like troubleshooting a regular circuit. All right, if somebody says, hey, my lamp's not working, well, let me check voltage at the outlet. There's 120 at the outlet. Okay, your lamp is bad. Or wait a minute, there isn't even 120 at this outlet. So I'm not concerned with your lamp yet. Maybe your lamp's broken. I don't know. But my first concern is, why isn't there voltage at this outlet? So once I establish that L1 and L2 are providing power to, if they don't, then I work my way back. Hit the transformer, work my way, hit the fuses inside of the disconnect. If there's no power at anything here, then we head north towards the panel. We keep working our way back until we hit the point where power has been lost. But assuming that I have power on L1 and L2, right? That's the first thing I want to establish here. Heading back over to the diagram that I had here. Okay, check, L1 and L2 have power. Now, if this pump is not working, well, something along the line has not engaged to provide power to the rest of things. All right, and that's all troubleshooting in motor control is. All right, it's follow, point to point, for those of you who did Code D with me. Point to point checking. All right, you check power from that point to that point. Do I have power? Yes, no. I have power? Good. This one is fine. Point to point. Do I have power between this point? Yes, no. I have power. Good. And then we continue down the line. Do I have power here? Yes, no, and so on and so on. Power here? Yes, power here. No power here. Okay, something's going on with this float switch. It's that simple. It really isn't any harder than that. However, as I said, that's on paper. Now find the float switch, find the pump, find these wires, troubleshoot the wires. So there's the hard part. Ladder diagram helps us the most of, now going back over to the list, of those three, I would say, in my opinion. Schematics a little bit out of the window of motor control, right? It's more so for machinery. But between wiring and ladder, ladder is the choice. All right, let's look at a couple more down here. One line block and flowcharts. These are not motor control related, but they are diagrams, so there is some use to them. We can jump over to the next figure, 2-6. By the way, if you had any follow-ups to the ladder diagram, feel free. All right, if you had any questions about, and obviously if you had questions about the components or how the pump works, we will explore that as we go through. You will be able to read that diagram that I just showed you with no problems, hopefully with no problems by the end. All right, let's jump over. Now I don't have any examples of these. I'm just going to use the ones that the bookers are giving us because they are more so for distribution of power. All right. Well, this one I should say specifically. This one line diagram is more so to understand the distribution of power in the circuit, but not specifically to troubleshoot. What do I mean by that? Well, let's look at the diagram. All right, as this note says here, a one-line diagram is a diagram that uses a single line. One line, single line. Very easy to understand that. And symbols. So everybody really uses symbols. I don't know why they're using the word graphic, but symbols. To indicate the path and components of the circuit. So this is a great little diagram if you're not familiar with everything that's in play in the circuit. Right? This one shows us a lot. It shows us the switch. Okay, we got a fuse. Okay, we got another switch, right? We got these two switches here. We have a control symbol or control panel. We have some push buttons. Then there's a motor. All right, I got an idea of what's going on here. Is it useful? Sure. In a sense, it's useful. One-line diagrams are always useful. All right, just to get the paragraph out of the way, line diagrams, and this is why very confusing, right? They're using line diagrams here. We go back one, here again. Very confusing. So we're going to use ladder. And I think everybody in the industry uses ladder. This is what I call a line diagram or a one-line diagram. Line diagrams are often incorrectly referenced as one-line diagrams, right? So line diagram, one-line diagram. Very confusing. Or not very, but somewhat. But a one-line diagram is a diagram that uses, as it's set up there, a single line to show us all the connecting points of the electrical circuit. They have only one line between the components. So here again, is this three-phase? I don't know. What size wires? I don't know. How big is that fuse? We don't know. How big is the motor? Not telling us that either. So useful, yes, if you're not familiar with all the components, but not so useful if you're trying to troubleshoot why something is not operating, right? One-line diagrams are one of the diagrams that I would like when I would first get hired into a building to be their industrial electrician. One of the things that, the first thing you want to start doing when you get hired onto one of these jobs is get familiar with the electrical distribution in the building. How many panels do I have? What do these panels do? You know, is this panel for lighting, or if it's for outlets? Is this one the one that deals with the motors, air conditioning system, etc.? Walk the whole building. And I've gone into buildings, I think I mentioned it yesterday, when I was working at that laundry facility, and it's the oldest building I've ever worked at, that's why I mentioned it. That laundry facility was 60 years old. So it had a lot of panels in there that, you know, have been changed around, moved around, added. If you ask for the blueprints, these blueprints are 40, 50 years old. So a lot of what's on those blueprints was a little bit off. So I walked the whole building, and I did that. I created my own one-line diagram by simply, you know, okay, panel, If the panel didn't have a reference number, I gave it a reference number. This is panel, whatever, A1. Panel A1 is for L, lighting. All right, made a note for myself. This panel is picking up its voltage from main distribution panel number whatever, B, etc. All right, so you can create your own one-line diagram the way I just did right here. Main distribution panel, panel A1 for lighting, and start to simply get familiar with all the panels in the building. Now, newer buildings have this in the blueprints. Right? All blueprints have a set of what we call one lines. The one lines show us exactly that, all the panels and everything that the panels take care of. So it's a great diagram when you first show up on a job site and you want to get familiar with all of the components in the building. All right, now the other two, block and flowchart. These are technically not diagrams in a sense. Well, flowchart is a chart. So they do call it flowchart diagram in the book just to continue with the diagram, but it's not really a diagram. Let's jump over to block diagram. You can find it on figure 2-8. All right, figure 2-8. All right, give everybody a beat to get to that. So let's take a look at what it says. Now, for my folks that are going to get into electronics, all right, if you go further into component level, all right, electrical has, you know, it's like a tier of how small are you going. All right, if you know, linemen, right, the people that work on the utility, big voltage. Electricians work on smaller voltage. Motor control, even smaller voltages. Electronics, even tinier voltage. So it's like a tier of getting into lower and lower and lower and lower voltages. So for those of you who like electronics, want to get into electronics, you know, we do at the school, I believe, offer the bachelor's in electronics. Maybe it's an associate, I'm not sure there. But there is component level troubleshooting, right? We don't, as standard electrician or motor control electricians, we don't do component level troubleshooting. What do I mean by component level troubleshooting? A circuit board, right? And figure out why the circuit board and the rectifier or whatever all these little components are on the circuit board, I don't know all of them, why they aren't working. But if you did, then the block diagram is your best friend. All right, just to read the paragraph down here, block diagram shows the relationship between individual sections, or what they call blocks, of a circuit or system, but specifically for electronic components. All right, these block diagrams are intended to show you the current flow, what direction the current is flowing in the circuit. All right, just to continue reading here, block diagrams are used with schematic diagrams to help troubleshoot a system, such as regulated power supplies. All right, power supplies like the one that converts AC to DC. So all of this I've consolidated into a small note. Block shows the current path in an electronic circuit. All right, and if you look at the actual block that they're showing us here, you can see, oops, sorry about that, you can see an arrow. That arrow is showing you exactly that. Direction the current is flowing into this system. Transformer to rectifier, rectifier to filter, filter to voltage regulator, and then out to a voltage divider. All right, so this is a very useful diagram for electronics, but like I said, we do not deal with electronics that much, so in many ways, block diagrams are out of the world that we're in. Now, last but not least, and it is 8, so I do want to get into the next part of this chapter, we get to a flow chart. All right, a flowchart is a diagram, not really, that shows the logical, and here's the word logical, not logic. This is one of those questions that you hit in an exam and you can get a little bit confused. All right, it also uses the word troubleshoot here, which is, again, a little bit confusing. Is this, because that seems like a ladder diagram. If I told you the ladder diagram shows us the logical sequence of steps to troubleshooting, well, then that sounds like what a ladder diagram is. But it's different. Logical path versus, going back over to the ladder, logic of the electrical circuit. Right? The ladder diagram is focused on the electrical circuit. A flowchart, and maybe you've used one of these before. I had a student a while back that worked on military vehicles, I think Humvees or something like that, and they used a flowchart. All right, so I have my note here that kind of helps. Shows the best direction, logical path. That's why they're using the word logical here. Not logic of the circuit. Now it's just logical. What makes sense to do next? Logical path to take when troubleshooting. So a lot of machines come with these, especially newer machines or new enough machines where we've kept all the paperwork that comes with the machine. When you first get a machine into the building, they give you a lot of stuff with the machine. They give you a ladder diagram on paper. They give you it in a USB port as well, so you can pop it into a laptop and be in front of the machine. Sometimes they give you a disc, but I don't know if discs are showing up anymore these days. But they also give you a flowchart because it's a new machine. So how do I troubleshoot this machine? I've never done it before. So you head into the flowchart just to look at the example they have here. This one is for checking power. It seems very straightforward, and so you go, okay, just follow this one. Again, it is very simple, but it is what it is. Is power to the motor off? I think this is part of PM or preventive maintenance for this. No, turn power off. Yes, head to the next thing. Once you turn power off, then we go to check to ensure power is off. Is there damage? Yes, there's damage. Okay, head to the path that you need to take if there is damage. If there is no damage present, then you go into the no section. Thermo switch is tripped. Yes, reset. No, power, measure, voltage, motor, terminal, etc. All right, flowcharts are quite useful components. They are super duper helpful if you've never done any troubleshooting on that machine. All right, but what did I say earlier? I said earlier that, and by the way, they're saying all that down here in the paragraph. Flowchart, logical sequence of steps for a given set of conditions. Flowcharts help somebody troubleshooting follow a logical path when trying to solve the problem. But as I said earlier, we don't show up to new machines every day. You get familiar with your machines. You know which one your problem machines are. You know which ones are great. You don't have to worry about them. They never give us any problems. So once you've been at that machine a few times and they've called you over, hey, the machine's not working, hey, the machine's not working, you kind of get an idea about that. That's why I said, if you still have this paperwork, because 9 times out of 10, after a couple years or after a year, that thing has been lost somewhere in the maintenance office. Right? Do we keep them? Sometimes. Sometimes no. All right, so I have this set up in 2 ways, primary and support diagrams. All right, primary diagrams, get out of there. Primary diagrams are wiring, schematic, and ladder. Support diagrams are 1 line. We're going to ignore block. Like I said, it is part of electronics, and flowchart. In many cases, you start with a 1-line diagram. Okay, got an idea of the whole overview of everything. Then you grab the ladder diagram and you start to troubleshoot. But first time walking up to this machine and troubleshooting, so let me go ahead and grab a flowchart as well so that I know where to go what steps to take. Do this a few times, and then you have that pretty down packed. You know, first day on the job site, flow chart. 1 month on the job site, no flow chart. Excellent. Got a good thumbs up there. All right, follow-ups, questions, etc. Maybe, maybe not. All right, there's a little checkpoint, and this book has these little checkpoints. I don't usually do them in the classroom. There's no real sense in doing these. We are going to have a quiz, a homework. We have exams, so we get to do plenty of these questions along the way. But feel free. This one is not too difficult. I mean, this was on diagrams, so not too complicated. But always feel free when we get to these checkpoints. Just take a mental note. Come back to them when you get a chance, and see if you can answer them, or at the very least, go through them and then fall back into the chapter and be able to answer a couple of them, right? There's some details here that we should know, like logical path. Okay, this is about a flow chart. Length, height, object of an object, pictorial, right? Because no other diagram shows you the length, the height of anything. All these were wiring. All right, symbols for interconnection of electronics, right? That was a block. All right, so you can definitely do these checkpoints along the way. This one not too necessary. All right, if there's no questions, then let's head into 2-2, the next part of this, electrical circuits. All right, so objective, right? What is the objective of this side of things? Well, this objective is to state the 5 basic components of a, I don't know why they use basic twice, electrical circuit. All right, understand how to draw a circuit using symbols. And then we can ignore the manual control automatic. But we will eventually, and again, we'll see how far we can get down the line today, because I am going to go right into symbols now. We'll talk about solenoids, we'll talk about contactors, we'll define magnetic motor starters as we go into this. And then we are going to be talking troubleshooting a lot. So when it says here, explain how prints are read and how they are used to troubleshoot, we're going to do this along the way. All right, we're not just going to focus on troubleshooting right now because this chapter is telling us. We're going to do this along the way. So before we get into the first image, which takes us into the 5 components of an electrical circuit, let's fall back for a second and let's look at symbols. All right. Now, I skipped over symbols. This is why I'm falling back for a second. It was image 2-2, continued, and continuous. They did have a lot of symbols here, but honestly, I don't like any of these symbols, maybe 1 or 2 of them. No, I mean, I don't not like the symbols as far as for you guys in this classroom in motor control. There are better symbols that you should be looking at, specifically the ones that I posted for you, that have all these switches, limit, foot, relays, pressure, liquid level, temperature, all the different types of switches that we have. But let's go back one and take a look at these notes here. Symbols in motor control. Now, believe it or not, this is very important that you understand already. All right, these symbols are for motor control circuits. Well, what's the difference? Well, these symbols are not for PLC motor control circuits. PLC has different symbols. All right, motor control circuits have their own symbols. Next module, when you guys get into PLC, I think everybody's going into PLC next module, I assume. I did get some people from Code A jumping into motors and Code D into motors, so sometimes I don't know what direction you guys are going, but just assuming you haven't done PLC yet and you're going to go do PLC. The symbols in a PLC program, because that's what you're going to be working with, all PLC systems have a program that they work with. Allen Bradley, major component. Siemens, that's the other one. That's like that's the industry standards. Either you're using Allen Bradley or you're using Siemens, and then some lower ones along the way when you're not, have a massive motor control circuit. But these are the two. So those come with a program that you build your diagrams with. I have the program here. My computer is just hard to pull it up, but it's a lot of drag and place into a ladder diagram. All right, so you don't have to draw it out. The ladder structure is already built for you in the program, and you just drag and label all the symbols, and they're different from ours. This first note here might seem obvious, but therein lies the major difference between a PLC motor control diagram ladder structure and a motor control ladder structure. All right, now I'm saying PLC motor control but we just call it a PLC ladder diagram versus a motor control ladder diagram. In a motor control diagram, our symbols represent physical components. All right, symbols, that's what I meant here, are used, right? I just kind of shortened that. Symbols are used in electrical diagrams to represent physical components. Meaning, if I see it on the diagram, I should be able to find the physical part in the machinery or wherever. But if it's on the diagram, there should be a physical representation of this thing. PLC is different. There's a lot of things internal that the computer does that there is no outside physical component for. One example is the timing function. All right, just to give you a quick, we haven't even gotten to timers yet, but the timing function is very simple, right? If you press start on the motor, right, I press start, the motor doesn't start immediately. The motor starts in 5 seconds, giving some time for maybe a horn to sound or some lights to flash, letting everybody know, get out of the way, this thing's about to start. That's called a timing function or a time delay function. I press start, motor doesn't start, starts in 5 seconds or 10 seconds or 20 seconds. In our module, in motor control, we have a physical timer. Right? We have one, a little physical timer. Going back over to the board. All right, here's our timer here. I'm going to try to isolate it, but there's the timer. There's the little timer right there. So if the motor didn't start in 5 seconds, or if you want to change the motor from 5 seconds to 10 seconds or 20 seconds, you go to this timer, you change the little dial physically. Or if it's broken, replace, remove, replace. Or if you got to change anything else, all physically done on the timer. But PLCs have an internal timer. Meaning, if you want to change that from 5 seconds to 10 seconds, you got to pull up the laptop, pull up the program, get in there, and change it physically. If there's a problem with your timer, you go to the computer. You don't go to a physical timer. So when you're looking at a PLC ladder diagram, hey, there's the timer. All right, it says timer number 1. And I look at the wall, I got no timer. So to be able to troubleshoot a PLC-driven motor control circuit, you have to understand how to get it into the computer. All right, different from what we're looking at now, there we go. Where if I see a timer on my diagram, there's a physical timer somewhere on this wall. All right, so that's the first thing. Physical representation of components. Very important that you understand those two differences between our two worlds. Now, the next one is just an added note that I wanted to add. Not real important that you know this, but one of the good things about motor control symbols is that they're universal for the US, something that is not the case for blueprints. All right, blueprints, what we build buildings to, are different. The symbols there, like symbols for an outlet, and symbols for a switch, symbols for a GFCI, AFCI, the lights, exit signs, etc. They have no universal system, meaning whoever is using, AutoCAD or engineering the blueprints can decide any symbol for anything. All right, so they can make a switch a triangle and just say this is a switch. So that's why blueprints have a legend, All right, a legend that tells you what on earth is this symbol? Oh, it's fluorescent lights, or oh, it's an exit sign. I remember one time I looked at a set of blueprints and they had that symbol, and I was like, what on earth is that? It was the exit sign. Before, I've seen them different, something like with an E. Okay, is that an emergency? No, it's an exit sign. All right. So blueprints have to have that legend because they're not regulated. However, motor control symbols are regulated by NEMA, which means they are all the same in the US. So any set of motor control diagrams that you pull up are going to have the same symbols, again, regulated by NEMA. All right, this is why I'll be right back to this. This is why I was a little bit confused with this one because, you know, same, but a little bit different. All right, this is a little bit off. Not major, but a little bit off to our standard symbols that we have here. These are the standard universal symbols. All right, we'll go to that page here in a second. Now, all of the symbols are universal and they're all the same, meaning if I have a push button and the push button is, let's say, normally open the way this one is here, if I have 2, 3, 4, 5 normally open push buttons on the diagram, it's just one symbol for all of them, right? There is no other, for example, pressure switch. That's what it looks like. There is no other pressure switch symbol that I can use. So if I have 5 pressure switches on my diagram, every one is going to look the same. So going back over to my notes here, last note that I have is very important that we label our symbols. This is something that I'm going to be looking at when I look at your diagrams that you guys turn in. Please make sure you label everything. All right, start button, stop button, motor starter, coil. You can abbreviate, all right? That's why going over to the, that's why, now this one says motor start. Do you have to? Can you put start? Yes. You could also just put PB1, PB2. That would be fine as well. Instead of motor starter coil, M1 is fine. So however it is that you want to abbreviate and address it, one of the things that is allowed in motor control is to label however you want to label. That is okay. But please provide that. An abbreviation, letter or numbers, doesn't matter. The form of letters, combination of letters, numbers would be fine as well. I don't have numbers here in the note, but numbers would be fine too. Like if you have multiple motors, well, then we have M1. I have another one. That one's M2, M3, M4, representing all of the different motor starter coils. So not only does the abbreviation of some kind used, as it says here, to identify the type of device that I have, it also gives me any associated components with that device. All right, any associated components with that device. I'll be right back to this, but let's go look at what I mean. Yesterday I pointed this out, but let's go look at it one more time. I have this M1 coil. This coil has an associated component, that contact, also labeled M1. That coil also has another set of associated components, also labeled M1. You'll notice not everything is labeled M1, only the things that are associated with that coil. M1 over here, M1 over here. But here I got X1, X2 for my transformer people. The start button and the stop button have no M anything. These are F1, F2, F3, F4, L1, L2. So everything has its own label, its own abbreviation, its own set of information. And this is so that, again, look at this one here. I have 3 circles. Let's say I did not have that information. Well, then I just have 3 circles. Which one's the pump? Which one's MCR? By the way, that's motor control relay. CR is just control relay. So which one is CR? Which one is MCR? Which one is the pump? I don't know unless I have abbreviations in the form of letters with numbers if you want as well, right? So now I know this MCR, associated component with MCR. CR1, associated component with CR1, associated component with CR1. And why do we want to know that? Well, if, let's say for example, it's always troubleshooting. Everything that we're talking about is about troubleshooting the machinery, not building. Again, as I was saying yesterday, 90% of this job has nothing to do with building the circuit. It's about troubleshooting the circuit. So if I want to know why this pump is not on, well, stop number 1 is that control relay contact. Why haven't you closed? Well, control relay contact is going to say, I'm not responsible for closing me. The coil is responsible for closing me. How do I know it's that coil? Because CR1, right? This one is MCR. So the letters and the abbreviations, without them, again, we live and die by these diagrams and being able to make sense of the circuit through the diagram. So if you don't have a good representation of those components, then people will be lost. So that's what I'm going to be looking for in the beginning, for online and in person. I want to see the diagrams. I want to see things properly labeled. And just to get you in the habit of it. PLC, when you get into that, it'll be much easier because you're going to be using a software that kind of does a lot of the things for you, but you still will be addressing things in that sense. Let me just see where we're at. Okay. All right, so these are all our, I should say, all of our physical devices. The only ones that aren't here are sensors. Right? I don't have sensors here, but sensors do play a larger role in motor control. But I would say sensors work more when there's a PLC involved. Sensors and standard motor control circuits don't really function too well. Sensors are very sensitive pieces of equipment, and they like to communicate with a computer. So all you have to know about these symbols right now, all right, we'll get more familiar with them when we get into week 3 and we get into the chapter that covers motor control devices. So right now I just need you to get familiar with 2 terms, which my folks that did Code D with me hopefully remember it. But normally open, always represented as no or NO, normally open. Let me clean that up a little bit. And normally closed. All right, normally open and normally closed. 1 second. Let me just see. Okay, no, I don't have that. I'll put it here. So, whenever you get a device, you can either buy the device in the normally open position, or you can buy the device in the normally closed position. Now, when we get into chapter 5, we're going to explore a little bit more as to which one do we need and when do we need it. All right, because there is some rules to normally open and normally closed, specifically with putting things in series and when you wire things up in parallel, right? So that's covered in chapter 5, relay logic. By the way, that's what we are in this module. We are RLC. Next module is programmable logic control. We are relay logic control, but it's not really used as much. PLC is the one that everybody uses, so RLC kind of gets forgotten, but that's technically what this module is, RLC. So again, when we get into chapter 5, we'll explore more when we have to use one versus the other, but right now all I need you to understand about normally open and normally closed is what the function of closed and open do. If you are an open switch, right, doesn't matter which one we limit switch, proximity, flow, foot, liquid, doesn't matter which one we say. If you are an open switch, voltage is not going across you right now, right? You are a open switch. Same thing for our push button. It just has a different symbol. Little top hat. If you are in the normally open position, voltage has not gone across to the other side of the switch yet. If you are in the normally closed position, then yes, right? Because it's closed. Push button, closed. Any of the switches, doesn't matter. Closed. If you are a normally closed switch, then voltage is going through you. All right, and then sending voltage to whatever is down the line. So right now, that is one of the first things that I want you guys to start to do when you start to look at electrical circuits. In the book, electrical circuits, excuse me, or ladder diagrams really. Whether it's in the book, whether it's in our labs. First things I want you to start to do is, and I'll use this wiring diagram as an example. Well, we can use this one, but we'll use the wiring diagram as an example. Because it technically is lab 1 for everybody. The bottom part. Where is voltage? This is what I want you to say to yourself. Where is voltage right now, and where isn't voltage right now? All right, by the way, let me go. I'll be right back to this. Let me go right back over here. There is one more symbol, which is the contacts right there. Normally open, let me just make sure I'm not in the way. No, I'm good. Normally open contact looks like that. And the normally closed contact has a line across it. So a normally closed contact is allowing voltage to flow through. Normally open contact is not allowing voltage to flow through. So again, in the beginning, ask yourself, when you look at a diagram, any one of them, when I pull one up, when you look in the book, again, in your labs, where's the voltage right now, and where isn't the voltage right now? And it starts to give you an idea of how to, as always, troubleshoot this thing. Right now, assuming there's power here, these switches are closed, as I was pointing out yesterday. Meaning voltage is here, but we run into a normally open contact. So it's not on this side right now. All 3 of those phases were good. There, voltage is there. Voltage going into the transformer, again, assuming the transformer is fine. Voltage, and we're going to ignore here because not really voltage, but hot. Stop button, normally closed, voltage goes through. Start button, normally open, voltage pauses. Connected to this same line, voltage going down, normally open contact, voltage stops. So right now, here is where voltage is and where voltage isn't. Right now in this position, this coil has no electricity here. Now, the opposite, right? The next thing to understand about normally open and normally closed is what happens when we engage the device. If I press the normally open push button, then yes, when you press the normally open push button, it provides power. If this contact were to close, then it sends power. If these contacts were to close, then the motor starts. So I just gave you your first set of tools for troubleshooting. If something hasn't started, right, if the machine hasn't started, one of the first places you want to start troubleshooting is find your normally open components in the circuit and figure out why they didn't close yet. Looking at the pump now. Pump hasn't started. Uh-oh, pump's not working. Well, why hasn't this contact closed? Well, this thing should have gotten power. Relay coil. That is a normally closed float switch. Is it open? If that's open, then no power down the line. All right, so that's the beginning. Beginning of piecing this thing together, understanding the position of the switches, open versus closed, and then what that represents. No voltage into the system or yes voltage into the system, and then the next phase of that, which is why hasn't this started or stopped, right? If this thing is not stopping, then something that is closed is in the open position, or sorry, something that is, closed has remained closed. It's not opening, etc. We got 2 minutes, not going to worry about this right now, but last but not least is going to be getting into the versus, push buttons versus industrial switches. All right, we do have some manual things that we'll get into. All right, we're good here. I'm going to pause it right there. Don't want to keep you guys too long, but I think we're good. All right. Now, any questions following up with